Hi, my name is Hyonjee. I'm a software engineer at 2 Sigma, and today I'm going to be talking to you about Greenhouse, a distributed Spark application for batch testing research ideas on time series at scale. So before I start, I have to throw a quick legal disclaimer up that basically says I'm not going to give any financial advice in this talk. A little bit about me. I have a degree in computer science and psychology. I love to travel and hike mountains. This is actually a photo of me climbing Teapot Mountain in Taiwan just a few weeks ago. And I'm currently a software engineer at 2 Sigma building scalable analytics solutions for researchers. 2 Sigma is an investment management firm that uses technology and lots of data to drive investment decisions. And I focus primarily on leveraging distributed compute and open source tools to make all sorts of research possible. In the next 15 minutes or so, I'm going to be giving you an overview of the technologies and tools that I use to build Greenhouse. I'm not going to go into any one of them in too much detail for time's sake, but if you're interested in discussing more about any single technology that I mentioned, please come find me after the talk. To give context to my talk, I'll begin with a high-level overview of what research at 2 Sigma looks like. We usually start with lots of time series data, or data ordered chronologically by time, and we research this data to find trends or insights to build models that can predict future market movements. Once we have a model that we've tested and know to be true with some degree of confidence, we'll use the model's predictions to make investment decisions. This process is pretty iterative, and we always have new research ideas and data sets that we want to test. So that brings me to the first main point of my talk, which is that testing hypotheses at scale can actually be really challenging, and I'll show you why. So we use the scientific method in our research to make data-driven decisions. As many of you all know, the scientific method usually starts with some observation, then the formation of a hypothesis. You test that hypothesis with experiments and data, and you can accept or reject that hypothesis, and based on the results, you might repeat this process all over again. So how does this apply to our research at 2 Sigma, you might wonder? So let's go through a hypothetical example. Let's say we observe that avocado prices seem to be linked to Bitcoin prices. This is actually a graph of time series data recently published in the Bitcoinist. On the x-axis, you have time, and on the y-axis, you have prices. The green line represents avocado prices, and the white line represents cryptocurrency prices. And you can see that the two prices seem to be linked over time. Then our hypothesis might be that when avocado prices increase, cryptocurrency prices will also go up. We formulate a model that predicts market movements based on our hypothesis. So in this case, a model that says when avocado prices go up, cryptocurrency prices will also go up. And then we test our model using simulation and years of historical data. If our experiments turn out well, we might productionalize our model for trading. If they don't turn out well, we'll form a new hypothesis and repeat the research process. So while the scientific approach we take is very thorough and helps us discover more reliable and robust models, the trade-off is actually that the process can be very time-intensive. It could take hours and hours to manually test a single hypothesis, and perhaps months to find a promising result. In practice, we have thousands of hypotheses we want to test using thousands of data sets. With research, you often find that you end up testing a lot of ideas before you find something that holds to be true. So you can imagine why we'd want to accelerate our research process. The solution to this was actually to automate parts of our research process, to be able to test more hypotheses and discover more promising results. We built a system where researchers could submit their hypothesis and input data sets into an analytics engine or a platform that could run common workflows in the data analysis that the researchers would otherwise be doing manually. The analytics engine then writes the results or analysis into a data store. So that way, the results can be used later to generate predictive scores or results that indicate how promising the research idea was that the researcher wanted to test. So the purpose behind this automated research is to be able to test more ideas and to filter out the good ideas more quickly, so that way researchers can spend their time digging deeper into the data sets and the hypotheses that are the most interesting. In this talk, we're going to focus on how we built this analytics engine, which we call Greenhouse. Greenhouse is the engine that powers this automated research process. It helps researchers grow their seed ideas faster and cultivate results more effectively, hence the name Greenhouse. So in this next section, I'll walk through how Greenhouse works and how we built Greenhouse, specifically using Apache Spark for batch analysis of time series data. Conceptually, Greenhouse is a workflow engine that runs common data science workflows in our research process. Users provide the input data they're interested in researching and make requests describing the type of analysis they want to do and the workflows they want to run on their data. This input data is a time series where time is the ordering key, and usually the data describes some real-life set of events. Greenhouse is capable of running a number of workflows that analyze or transform this input data to yield informative results. So, for example, one of our workflows joins input events data with relevant market information, so that way we can see whether or not the events drive or have any effect on market conditions. The result of this analysis, or the output of running the workflow in Greenhouse, is then saved in storage and used by researchers to guide their research going forward. The reason why we use the term workflow engine is because Greenhouse processes several user requests and input data sets in parallel and runs tens of workflows at once. In order to power this high volume of data analysis, we built a robust and scalable platform using a number of open source technologies. So I'll be giving an overview of what those technologies are and explain how they all fit together to make this automated data analysis possible. The first one that I'm going to talk about is Apache Spark, one of the fundamental building blocks of Greenhouse. Apache Spark is an open source distributed compute framework that provides an interface for working with distributed data sets in a parallel and fault-tolerant manner. In Greenhouse, we use Apache Spark to run the workflows that I was describing earlier. When we do our data analysis with Spark, Spark distributes our computations, making our workflows very fast. And we've also designed our Spark application to run many workflows in parallel, increasing our throughput. And to show you how this all works, I'll do a deeper dive into Spark. So this is a close-up of a Spark cluster. Every cluster consists of a single driver program and several executors running on worker nodes. Each executor has a local data cache and can run many tasks or threads in parallel. The Spark driver schedules jobs and distributes tasks and data partitions among the executors, so you can think of the driver as the master coordinator in the Spark cluster. In Spark, data is stored in a resilient distributed dataset object, or an RDD object. Here, for example, we have time series data from January to June of 2019 stored in an RDD, or specifically a time series RDD. The data is partitioned by time and distributed across all of the executors. Each executor operates on its data partitions in parallel by running tasks assigned to it by the driver. Usually, the number of running tasks in an executor corresponds to the number of cores on the machine. Tasks are retried if not successful, making the whole system pretty robust and resilient against transient failures. In this close-up, we have a 2-executor Spark cluster with 4 cores in total, but in practice, we run Spark clusters that have many more executors and hundreds of cores. So in Greenhouse, the same Spark cluster is also shared amongst many researchers to run common workflows. This increases overall efficiency and throughput. Instead of users starting their own Spark cluster every time they want to run a workflow, we keep a Spark cluster up and running with hot data caches in memory that have hundreds of gigabytes of data loaded and ready to use. And we find that most of this in-memory data is common to all of the research workflows, so that way it's reused across multiple user requests. Using a persistent Spark cluster with persistent data caches means that Greenhouse can power the analysis of thousands of input tables, making efficient use of our compute and storage resources. So now that we've seen how Greenhouse is powered using Apache Spark, you might be wondering, how are these workflows actually implemented to run on Spark? The workflows in Greenhouse are actually implemented using Flint, which is a library that enhances Spark's functionality for time series data. So to put in other words, Flint is 2 Sigma's open source library for specialized time series operations in Spark. At a high level, Flint does this by taking advantage of the data's natural time ordering and providing operations that take advantage of data locality in Spark executors. So we've really fine-tuned the operations to be very performant for time series data in particular. So to see how Flint works, because the description I gave is very abstract, let's take a look at the workflow that joins events data with market information, the same example that I showed earlier, and see how Greenhouse uses Flint's temporal left join to make this join happen. So in this workflow, our input data set, or left table, is sparse events data. So what this means is that it's an irregular time series of when events happened in time. So you can see that the timestamps don't happen with any regular frequency. On the right side is a time series of market data reported at regular intervals. So here we have market data that seems to be reported once a day. Every day the market is open, Monday through Friday. So joining these two data sets together can help us make connections between the events and movements in the market, which will ultimately help us do our research. When we join these two tables together, we use time as a join key. And in Flint's temporal left join, what this means is that for every row in the left table, we'll look for a row in the right table that has a matching timestamp. If there is no matching timestamp, we'll look backwards into the past to find the next most recent row. So going back to our example tables, this means that the Saturday, June 8th event would need to be matched with the market data from Friday, June 7th. There's no market data on Saturday, June 8th, so that's why we look back into the past to find the next most recent row, which is from June 7th. The result of this Flint left join is a join table that has relevant market information for every event that we observe in our left table. Under the hood in Spark, the data is stored in Flint time series RDGs, which are partitioned by time and distributed across the Spark executors, preserving time order. So in this illustration, we have two data partitions in our left table and two data partitions in our right table. Flint then constructs a directed acyclic graph that maps these data partitions based on which partitions would be needed to join together. Here again, we see that the Saturday, June 8th entry on the left needs to be matched with the Friday, June 7th entry on the right. And so the bottom left and the top right data partitions are both mapped to the same join partition. Flint then executes this join on the fly in a streaming fashion, and it's very performant. Greenhouse uses several other Flint operations, like the left join, to implement efficient time series workflows for distributed time series data sets in Spark. Flint enables us to implement fast workflows, but our users also have an ever-growing number of data sets and ideas that they want to test. So it's always, can we get more throughput? We want to test more ideas, more data sets. So our next challenge was to figure out how we could scale Greenhouse using Spark to get even more compute and analysis done. So in this next section, I'll talk more about how we address this demand to scale and introduce you to the technologies that we use to make this happen. So when we began our quest to scale, we actually started by performing benchmarks on a single Spark cluster. So how much throughput can I get from running one of the Spark clusters that I showed earlier? And some of our findings are pretty interesting. First, we tested how we could get more throughput if we increased the compute in our Spark cluster by vertically scaling, so increasing the size of each of the executors. If you remember this diagram that I showed earlier of a Spark cluster, you can imagine vertical scaling by taking each executor and giving it more CPUs and more RAM. What we expected or hoped for was more or less a linear relationship between the amount of compute and our throughput. But what we actually saw was this. The throughput plateaued fairly quickly. With vertical scaling, we were supposed to have more cores and more memory to process more requests in parallel, but each executor was still limited to sharing the same physical resources on the same machine. So next, we benchmark request throughput as we increase the number of executors, so by scaling our cluster horizontally. That means in the Spark cluster here, I would have more executors running side by side. Again, we wanted to see more or less a linear relationship, but what we saw was this. The throughput trend was more promising, But the high amount of parallelism needed to keep all the executors busy eventually put a strain on our single Spark driver. So that became the source of the bottleneck, and we couldn't get any more throughput. So because of these limitations of scaling a single Spark cluster, we actually invested resources in scaling Greenhouse to have multiple Spark clusters. So we went from 1 to why not run 3 or more side by side. We wanted to be limited by how much we wanted to spend on compute and not necessarily by any technological limitations. So to see how we could get from 1 running Spark cluster to multiple, let me talk a little bit more about how we run and manage a single Spark cluster. So we actually manage our Spark clusters in Greenhouse using Kubernetes as a resource manager. Kubernetes is an open source container orchestration system that handles application deployment, scaling, and management. So what that means is that Kubernetes will keep our Greenhouse deployment up and running at all times. And if one of our servers crashes, Kubernetes will restart it for us. I'm not going to go into Kubernetes concepts in too much detail because there's actually a lot of documentation online. But generally speaking, we have a Kubernetes deployment for Greenhouse where we specify how we want Kubernetes to run our application. In our deployment, we specify what we want our pods to contain. So a pod in Kubernetes is the smallest replicable and deployable unit of compute. You can think of it kind of as a logical host that has its own operating system and its own storage. So inside of a pod, we can have 1 or more containers, which share the storage, network, and kernel resources of a pod. In Greenhouse, our pods have containers which run a Spark cluster, as well as other peripheral logging processes. So running on Kubernetes makes it easy for us to control how many Spark clusters that we want running to power Greenhouse. In the deployment spec, if we set the replicas to 1, like we have here, then we would have 1 running pod. But if I change the number of replicas to 3, Kubernetes will spin up 2 more identical pods, meaning that I'll have 3 running Spark clusters in my Greenhouse deployment. Similarly, if we scaled the number of replicas to 5, we'd have 5 running pods and 5 Spark clusters as a result. So it seems easy enough, right? So running Greenhouse on Kubernetes ensures not just that we can scale, but also that we have maximum availability and reliability. Again, if any one of our pods is experiencing issues, Kubernetes will notice that and automatically restart the pod and bring our Greenhouse deployment back to good health, which means our users will be happy. Our Spark clusters also run independently of one another, so when a user sends us a request, that request can be processed by any one of the running clusters. This means that the pod scaling can be done transparent to users, and users don't really need to care about how many Spark clusters we're running in the background. So how do users send requests to be processed, especially if we have multiple Spark clusters that are up and running? Users submit requests asynchronously to Greenhouse by writing request messages to a Kafka queue. You might be wondering what Kafka is. Apache Kafka is an open source streaming platform that is optimized for high throughput, low latency reads and writes. So every Kafka topic or stream has multiple partitions, each of which can be subscribed to by a producer for writing messages and by a consumer for reading messages. And these producers and consumers can read and write messages in parallel. So in our system, Kafka acts as a wide queue that can intake a high volume of requests. We also process multiple requests from this queue in parallel using several consumer threads. So these consumer threads can be distributed across multiple Spark clusters as well, and they can consume from the same topic. So in this example, I have 2 Spark clusters with 2 consumers each, and they'll subscribe to a subset of these topic partitions. Kafka also makes it easy for us to scale as well. Given the way the Kafka consumers work, we can actually scale up the number of running Spark clusters, and the existing topic partitions will be rebalanced to include all of the consumers, including the new ones that came up. So we can easily go from 2 running Spark clusters to 3, and the new consumers that join will just consume from the same Kafka topic by taking 1 or 2 of those partitions. So with Kafka and Kubernetes, scaling Greenhouse to be a multi-cluster Spark engine is pretty straightforward, and it's transparent to users, because users will just submit their request into the Kafka queue. They don't really care how many Spark clusters are running, but if we find that the queue is getting longer, we'll just spin up more Spark clusters and get the throughput to increase. Furthermore, we also run our Spark clusters in the public cloud, which gives us the compute bandwidth we need to scale. So the availability and the elasticity of compute in the public cloud gives Greenhouse the flexibility to match research demand as it changes or grows over time. Throughput is no longer limited by the technology then, but rather by how much we want to pay for compute. To end this talk, I'll give a quick glimpse at the results that we've seen with Greenhouse and how Greenhouse has impacted research at 2 Sigma. Since 2017, Greenhouse has processed over 3.1 million requests and petabytes of data to test millions of hypotheses. Some operations, like the Flint left join that we discussed earlier, was delivered a 100x speedup over the old methods that we were using. So research workflows that used to take hours now only take 5 to 10 minutes on average. This has been a pretty big step in accelerating important parts of our research pipeline. This is a snapshot from our metrics showing the number of requests processed steadily growing over time. Faster runtimes and greater throughput in Greenhouse have enabled us to test more ideas than ever before. And lastly, while Greenhouse as a research engine has done really great things, there's still a lot of demand to continue scaling and growing the platform. This chart shows a snapshot of the number of pending requests to be processed, numbering in the thousands. So there's really no shortage of ideas and data that researchers want to test. And there are always new ideas and requests being added to this queue. Greenhouse has been a pretty successful product so far, so we plan on further scaling and solidifying the platform to try to match this growing research demand, if we can ever keep up. So that was it for my talk. If you have any questions, feel free to ask them now or come talk to me afterwards or shoot me an email. Thanks.